Hi guys, welcome back. We are in the middle of related rates, and this is the second of three videos. I'm going to do three different examples today, three different types that I did in the first video, and the third video will have another three different types of related rate problems that you would be expected to see. Alright, so let's go with this. So car A is traveling west at 50 miles per hour. Okay, so I'm going to go ahead and do a road. So here's our little road in my, I can't not draw a car. What is that? There's my car. All right, yeah. So there's my car, and so this distance, he's traveling west, right? This distance, and we're going to call this distance x. All right, so we have a distance here, and this distance that this car is going is x. So first thing I can do is know that the change of x with respect to time is going to be equal to 50 miles per hour. And again, in the first video I told you guys you should probably read the question first before picking it apart, but I've seen these questions many times, so I know kind of what's going on with them. Okay, so there's our first little car, 50 miles per hour. And then car B is traveling north. All right, so traveling north. So here's our second car traveling north. And that's going to be a distance y. Right, we're going to call this distance y. And it's going 60 miles per hour. So change in y is going 60 miles per hour. So they're both headed for the intersection of the two roads. So that sentence actually makes a little bit of change we need to do. So they're going to the same intersection. So this road ends here and here. So we have to modify these two problems. I'm hoping before I tell you what I have to do, you already know what I'm going to say here. Since we're looking at this, so remember the car is originally here and it's approaching this intersection. This car is here and it's approaching this intersection. So what can I say about these rates as time goes on? And they're getting to be negative, right? They're negative because this distance is getting smaller with time, so our rate is decreasing. All right. Then the next thing is, at what rate are the cars approaching each other? So we can now go ahead and create ourselves another little thing. So this would be the distance for where the cars are. All right. And then obviously as time moves on, their rate is going to be changing. It's going to get smaller, so this number should also be small. So we're going to call this our z thing. So we want to know what's the change in z. All right, we're using the example that z is the distance between the two cars at any value of time. All right, and again they're approaching this intersection, which again we're going to assume is perpendicular. So at what rate are the cars approaching when car A is 0.3 miles and car B is 4 miles from the intersection? So as a little small picture of this, I want to know what happens when this distance is 3. So here's car A here, and then this distance here is 0.4, and this is car B. So I want to know what this is right here. And clearly, Pythagorean theorem, 3, 4, 5. So this is 0.5. All right, so we know what x is. We know x is this. We know y is this, and we know z is that. So clearly, right triangle. So we did one of the examples in the previous video, the third one, I think, or the second one. Second one, we talked about Pythagorean theorem. So remember, it's x squared plus y squared equals z squared. So my first thing is the equation, right? Write the equation up. The second thing is to write down everything that I know. And I told you guys in the second example that I'm going to go ahead and always, when I implicitly differentiate this, that I just go ahead for Pythagorean theorem, I go ahead and just do this. Because it's really 2x dx dt plus 2y dy dt equals 2z dz dt. So great, wonderful. We know that x is 0.3. So now this is where we start plugging stuff in. So we know that x is 0.3. We know the change in x is negative 50. We know that y is 0.4. We know the change in y is negative 60. We know that z is 0.5, and again, we found that by Pythagorean theorem, and they're trying to find, and again, I always like to, when I have this out, is this what we're actually asked to find? Is at what rate are the cars approaching each other? So again, we're making z this distance between them, right? Are they approaching each other when the cars are 0.3 and 0.4 miles apart? So that's exactly what we want to do. So I'm going to go ahead and start writing these numbers out. So this is going to be negative 15. This is going to be minus 24 is equal to 0.5 or 1/2 dz dt. And so dz dt is equal to 78 miles per hour. So that's the change of z with respect to time, 78 miles per hour. All right. So hopefully that's a good one for you guys. This is, again, when we're talking about things approaching each other. So remember that an example that I'm going to do in example 5, it's going to be kind of a little bit of twist on this problem. So we group 4 and 5 together. So whenever two things are approaching at a particular point, right triangle it. Pythagorean theorem is what you're going to use. It's just as simple as that. All right. So let's go and look at question number 5. All right, guys, let's go ahead and try question number 5. It says a balloon is rising vertically above a level straight road. All right, so we have our little road here. And then we have a balloon. And I think we're going to make it like a little hot air balloon. Yeah, there's my hot air balloon. Looks like a light bulb, but I don't care. There it is. So there's my balloon. And it's rising vertically. All right, so there's our first head. So it's rising vertically. And that means that that's y, right? The direction of y. I always do the xy coordinates over y. And so it's raising vertically at a constant rate of 1 foot per second. So the change in y with respect to time is going to be 1 foot per second. Just when the balloon is 65 feet above the ground, okay, so that tells us that y is 65 feet above the ground, a bicycle passes underneath it. So a bicycle is going to pass, and yes, there's my bicycle right there. Okay, it's passing underneath it, and going 17 feet per second. So this is our change in x. So change in x with respect to time is going to be 17 feet per second. I want to know how fast is the distance between the bicycle and the balloon increasing. Okay, so this is going up, and this is going to be the bike going this direction. So the distance we're looking at here is this. So again, we have ourselves a nice little right triangle. And so this is going to be our z direction. So I want to know how fast is the distance increasing, so I know that my change in my z is going to be positive. And that clearly makes sense because, you know, the balloon's going this way and the motorcycle bike is going this way. After 3 seconds. Okay, so a couple things that we have to do here. So now what I've written down, not everything's completely accurate, right? And hopefully you guys can kind of already see that I got to go back and start manipulating this a little bit. But for a second, let's just go ahead and say, okay, we got ourselves a little right triangle. So I know that Pythagorean theorem is going to be the equation that we're going to use here. And I'm going to go ahead, just like in the example that we just did, I'm going to do my implicit on these problems, like so. And so x, we're not given that. We don't know what x is. We know y right now is 65 feet. Hint, hint, not exactly. And then we don't know what z is. So we have really not very much going on in this problem. We know the change in z is what we got to figure out. Well, we are given the change in x and we're given the change in y. Okay, so that's positively we know what those two things are. So I'm going to do all of this. And nothing is zero, right? Nothing is zero because everything is changing. The bike's moving this way, the balloon's moving this way, their distance is getting bigger. And so I'm trying to find what dz dt is. So I'm going to go ahead and put that there. I know the change in y. The change in y is equal to 1. I know the change in x is equal to 17. Now, remember, ladies and gentlemen, that 65 does not go here because we're looking at this. 3 seconds later. So remember, we're at 65 feet initially. Well, 3 seconds later, we have to go 1 foot per second. That's the change the balloon's going up. So we have to add 3 to this y. So this has to be 68. So be very, very, very careful about that. We also can find x very easily, because if the bike is going 17 feet per second and we're going 3 seconds, so 17 feet is equal to 1 second, then what is equal to 3 seconds? Well, that would just be 3 times 17, which is 51. So x is going to be 51. Now that I know that this is 51 and I know that this is 68, I can use my graphing calculator and Pythagorean theorem this and find out what z is. And that value is going to be 85. And now we're happy because we have everything that we need to solve the problem. And to save us some time, I'm going to just write what dz over dt is. When you were to multiply these together, add this up and divide by 85, you get 11. And again, we're looking at units. Well, z, y, x are all the same units. It's feet per second. So the distance between the bike and the balloon at that time, at time equals 3, is 11 feet per second. All right, so this one required quite a bit of thinking. So when things are in motion, you have to remember to take that into account when you're looking at time. Okay, so let's look at question number 7, which is the third example of this video. So it says a 6-foot tall man walks away from a 15-foot tall lamppost at a rate of 5 feet per second. So first thing we're going to do is we're going to draw ourselves a lamppost, and we know that this is 15 feet. This one will not be Pythagorean theorem, by the way. You're like, oh, they're all of them. Yeah, this is not Pythagorean theorem. So 15 feet, and so we have a guy, a person, and they're walking away. Okay, we're walking away at a rate of 5 feet per second. So we're going to call this distance between the person and the lamppost, we're going to call that x. So as they're walking away, so this distance here is x. All right, so the distance between the lamppost and the person is x. So if we can just identify that, then we can easily say that, you know, he's walking away at a rate of 5 feet per second. Okay, 5 feet per second. So it says, how fast is his shadow lengthening? All right, so think about it like this. So we have a lamppost that's like this, and so the light is casting this way. So the shadow is going to be in front of the man. Right? Shadow's in front of the man. So think about it like that. Your light is behind you, and so if you guys can just imagine that, your shadow's going to clearly be in front of you. So we're going to make this our y. Right? I'm going to change that color because it's really hard to see that here. So the change in y over time. So this is going to be the length of his shadow. So the x is the distance between the person and the lamp post, and the y is going to be the length of the shadow. So y is the length of the shadow. So it's asking us how fast is the shadow lengthening 3 seconds after he starts walking. Okay, so we want to know what this is. So the first thing we have to do is come up with an equation to do this. The other thing that I actually did not put in my picture yet is that the guy is 6 feet tall. Okay, so I know that. So this is one of those things where students have to remember good old geometry again. So it's all about right triangles. Again, we're assuming that the light post and the person is perpendicular. So I'm going to redraw without any of the pictures. I'm going to draw just my lines. And so this represents the light post. This represents the person. This represents the distance between the two. And this is the shadow. So I know that this is 15. I know that this is 6. I know that this is x. And I know this is y. And I also know that these are right triangles. And so based on what you learned in geometry, these two triangles, this triangle right here, this large triangle, and this small triangle, they are similar to each other. And so by property of similarity, you can say that y over 6. So base of triangle over height of triangle is equal to base of large triangle, which is x plus y, all over height. Right? So it's going to be base of small. And so this will go right here is this triangle, right? So it's going to be base over height, or height, or it doesn't matter. You can flip-flop these as well if you want to. But base over height, and then this right here, this guy right here is going to be overall triangle, and that is going to be base. The base is x plus y, and then this height is going to be 15. So now all I have to do is actually just start simplifying by cross multiplying. I get this, and then I'm going to go ahead and combine like terms. And I can go one step further and just do that, right? I can just do that. And so there's my equation. That's it. That's awesome. There's the equation that I need to actually implicitly differentiate. So this one took a little bit more thought in getting there, but we're good because now all we have to do is implicitly differentiate this sucker. So let's do that. So this is going to be the change in y with respect to t is equal to 2/3, because the derivative of 2/3 x is just 2/3, dx over dt. It's asking us how fast, it's asking us how fast is the shadow lengthening 3 seconds after he starts walking, right? 3 seconds after he starts. So this problem doesn't need the 3 because the x is gone, right? If this had been like an x squared or something like that, then I would plug 3 in for x. X would actually be equal to 3. But, because that's how we define it, but because of this problem, there is no chain, there's no x to plug into, so we don't need it here. So it could be 3 seconds, it could be 15 seconds, it doesn't matter. It'd just be this change in x is 5, and so this answer is going to be 10/3. And again, because it's not a volume, it's not an area, then this units is going to just simply be feet per second. Okay, so that's going to be the first part of that question. All right, so that's the first part of the question. So this is part A. That's the answer to this first part. The second part to the question, is how fast is the tip of his shadow moving at this time? How fast is this moving? Okay, now this is where students get a little confused with this. So I want you guys to think initially. Okay, initially, if the guy is standing right here at the pole, the shadow is right here. Let me use another color. The shadow is right here because he's really right there. And so when he starts to move, the tip is actually the distance of x plus the distance of y. So when we're actually asking to solve this problem, so this is the part B, the distance of our tip, we want to know what the derivative of change of x plus the derivative of y with respect to time. So what we're looking for is the change of x with respect to time plus the change of y with respect to time. And just think about it for a second. As we're walking, the tip is changing based on how far away he's moving from the pole. And the shadow is obviously changing as well when he's moving far away. So these two are both factors here. So all you have to do is find the change in x, which is 5 feet per second. And we're going to add to that what we just found for the change in y. This is a good time for me to tell you guys that they would read with you. So in a multiple choice, or an FRQ where let's say you mess up the first part, you get this answer wrong, then they should usually read with you, and because technically then you would get B wrong, right? Because you're going to use the wrong answer. So I would read with you guys here and actually give you, the right answer. So if you got the wrong answer, but you got it wrong, doing the right steps, then you get the point, if that makes sense. So anyways, again, adding fractions that are, common denominators. So I'm going to go ahead and just do this without much thought. So 5 is the same thing as 15/3, 10/3, and so I'm going to get 25/3, and again, feet per second. Okay, so that is video number 2, ladies and gentlemen, and hope that makes sense. And we're going to come back for one more video with 3 more types of related rates. See you in the next one.